Good morning, everybody. Welcome back. This is, I guess you're probably watching this on Wednesday. I'm making it on Tuesday. And we have some problems to work out today, over the next couple of days, really, that are all about trig identities, simplifying expressions, actually maybe doing some triangle problems. But just want to welcome everybody back. Hope you had a nice spring break and you're getting back to work, ready to roll. All right, so I'm going to work out 4 problems today, and I'm keeping my Pythagorean identities handy because I think they might come up once or twice through these problems. The first the first problem we're going to do is from the beginning of the problem set on page 463 to 464, and the directions, and I'll go over the directions each time we do a different type of problem. The directions from the beginning of this section say, use the given values to evaluate, if possible, the other 4 trig functions. So in this case, we're given, in this example, which is what we're doing, number 9, we're given that the sine of negative x equals negative 2/3, and the tangent of x equals negative 2√5/5. So we have to figure out the cosine, the cosecant, the secant, and the cotangent. That's what we got to find. I might even write those down. To remind myself, we got to find all those. We have to find the cosine of x. We have to find the cotangent of x. We have to find the cosecant of x and the secant of x. And you know what? We also, believe it or not, we don't have the sine of x. We have the sine of negative x. So we've also got to find the sine of x. So let's say that as well. Sine of x down here. But we have to remember, lots of stuff to remember with trig. But one of the last things I think we talked about before we went on this break was sine of negative x and cosine of negative x and tangent of negative x. We talk about odd and even functions. It's not super important to remember which one's odd and which one's even, but the more important part is remember that when you have the sine of negative x, that is equal to, sine of negative x is the same thing. That's equivalent to the negative sine of x. So sine of negative x and negative sine of x are the same. So if sine of negative x equals negative 2/3, then negative sine of x also equals negative 2/3. So I'm going to say that. So if negative sine of x equals negative 2/3, that would mean sine of x would equal just 2/3. So I'm going to write that. Sine of x equals 2/3. Okay, got that sort of taken care of. Now I go to my triangle, my right triangle. And I always use my right triangle when I'm doing problems like this, when I'm trying to find the other trig ratios. So, and I remember SOHCAHTOA. Sine is opposite of hypotenuse. So opposite of hypotenuse. So this is going to be the opposite right here. Opposite over hypotenuse. Okay? So sine is opposite of hypotenuse. Now I use the Pythagorean theorem. And we're going to find the unknown side. So we're going to go 3 squared. That's 9. So 3 squared equals 2 squared plus, we'll call that a, plus a squared. And we solve this for a, we're going to get, 9 minus 4, is 5 equals a squared. So a would be the square root of 5. So that side there is the square root of 5. And that's going to help me find the rest of the trig ratios for this problem. So right now we can jump right into cosine, and we can say cosine equals the adjacent divided by the hypotenuse. But there's one thing we do have to remember, and that's the tangent is given to be negative something. So negative. So if tangent's negative and the sine is positive, that would mean cosine must be negative. Let me say that again. If tangent's negative and the sine is positive, that would mean cosine is negative. So cosine is negative. Cosine is negative. So it's the adjacent divided by the hypotenuse, and we know it's negative. And so that's going to be equal to negative, I'll do that in blue because I did that one in blue. That's going to be equal to negative square root of 5 over 3. That's the adjacent over the hypotenuse. Okay, so now cotangent. Cotangent, remember, is going to be reciprocal of tangent. And if we remember Chow, that's adjacent over opposite. So adjacent over opposite, and we know it's negative because the tangent's negative. So this is going to be equal to negative the square root of 5 over 2. And if we take the reciprocal of this, we would also get negative the square root of 5 over 2. Cosecant is the reciprocal of sine. So the cosecant would be 3/2. And then the secant is the reciprocal of the cosine. And so it's the reciprocal of negative root 5 over 3. So that's going to be negative 3 over root 5. But we have to rationalize that bad boy. So we're going to go 2 times root 5 over root 5. And we're going to get negative 3 root 5 over 5. And so that's how you do a problem like the first 5 or so that we have to do for this assignment, is we write down what we know, and then we draw the triangle, and we use SOHCAHTOA and Chow to figure out the remaining values. Also, we have to remember the negatives, like sine of negative x equals negative sine of x, whereas cosine of negative x just equals the cosine of x. Tangent works like sine. So tangent of negative x equals negative tangent of x. All right, cosine's the weird one. All right, now we're going to jump to another type of problem, but it's in that same set. And it is number 17. And it's really unusual, but it has a really weird notation that we don't see very often. It's the top of page 464. And the directions say, let me read it over here so my face isn't right in the camera. In exercise 15-3, fill in the blanks. Note, the notation x approaches c positive indicates x approaches c from the right, and x approaches c negative indicates x approaches c from the left. So in this example, it says as x approaches pi over 2, and then a little negative sign. That means from the left. As x approaches pi over 2 from the left, from this direction, then the tangent of x approaches what value, and the cotangent of x approaches what value. Okay, so I drew the graphs of the two functions, tangent of x and cotangent of x, here to remind us of what these graphs look like. And we definitely talked about tangent. Tangent does this, remember, and cotangent does this, okay? Now, and also the asymptotes are a little bit different. In tangent, the asymptotes are at pi's over 2. So negative pi over 2, 3 pi over 2, etc. That means like the tangent of pi over 2, remember the tangent of pi over 2 is the sine of pi over 2 divided by the cosine of pi over 2. Well, the sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So 1 over 0 is obviously undefined, and that explains why we have the asymptotes, remember, at pi's over 2. Whereas for cotangent was cosine on top. So cosine of pi over 2 divided by the sine of pi over 2. Well, cosine of pi over 2, that's 0. And the sine of pi over 2 is 1. And so that's why we're going through 0 at pi over 2 for cotangent. Let's go back over to what the problem's asking. What is tangent getting really close to? What is tangent approaching as x is getting close to pi over 2 from the left, from this direction? Now the other one would have been, this is from the right over here, but we're coming from the left. So as x is getting close to pi over 2, as x is getting close to pi over 2, the tangent is getting close to this dotted line. And it's going up. It's getting really, really close to, never going to get there, it's getting really, really close to infinity. So we say that's approaching infinity. The cotangent, as we're approaching pi over 2 from the left, it's interesting because we're actually going to get where we're going, because the cotangent graph goes right through pi over 2, 0. So it's actually approaching 0. It's getting close to 0, and it actually goes right through 0. So this one will be 0. And it's interesting because the cotangent, whether you're approaching pi over 2 from the right or if you're approaching pi over 2 from the left, you're approaching 0. Whereas on the tangent graph, because remember it does this, if we're approaching pi over 2 from the left, we're getting close to negative infinity. But as you're approaching it, I said that wrong. As you're approaching it from the right, we're getting close to negative infinity. But as you're approaching it from the left, we're getting close to infinity. That's what that symbol means, by the way. Approaching. Okay? We're going to jump and we're going to do number 29. 29. And the directions for 29, I think, are just to simplify. I think the directions for the rest of the problems are to simplify. I kind of skipped doing any examples for the middle, like 20 through 30. Those were simplified, but they were really match. So you had to simplify those expressions until you got one of the given expressions. I thought those were a little bit simpler than a problem like number 29. 29, the directions are to... Oh, I am doing one of those. Sorry about that. Ha, ha, ha. This is 29 is one of those matching problems, but it's not very hard. What I'm going to look at, first of all, I got my Pythagorean identities over there to help. I have secant squared minus 1. And now one thing I could do, I guess, I could put 1 minus cosine squared in there, but then that would just get ugly for sine squared. That would make it uglier. So instead, I want to look maybe at this identity. And if I can say, oh, subtract that 1, I get secant squared minus 1 equals tangent squared. And so I can take this expression and put tangent squared in for secant squared x minus 1 divided by sine squared x. Well, tangent squared divided by sine squared, let's work that out. That's going to be sine squared x over cosine squared x. Well, that's pretty bad. Cosine squared x over sine squared x. And if I flip that, the sine squared x's are gonna divide out, and we get 1 over cosine squared x, and that is equal to secant squared x, which I think is one of our choices. Yep, it's choice E. Okay, that's how you do those. Actually, that's a good example to look at for problems like 20 through 30, really. Those, if you understand what I'm doing there, I think you can do fine on those. And the last example I'm going to do is we're going to jump down to number 49. The problems that you have to do, like 46, 48, 50, and 52, they all involve some kind of factoring. Yeah, they all involve some kind of factoring. So you're going to look at this guy. Tangent to the fourth, x plus 2 tangent squared x plus 1. And you're going to try and factor that somehow. Well, factoring is our favorite thing in the world to do. And hopefully we see something squared here plus 2 times a product and another thing squared. And so remember the 3 questions we can ask. Is the first term a perfect square? And if the answer to that question is yes, and it is yes, we say, what is the square root? Well, the square root is tangent squared x. Is the third term a perfect square? And if the answer is yes, and it is yes, we write the square root of that down, 1. Then we say, is the middle term 2 times the product of the 2 square roots? And the answer is yes. So what we do is we put a plus sign, because we put that sign in there, right there, and then we quantity square. So now we have tangent squared x plus 1 quantity squared. Well, tangent squared x plus 1, oh, that's right there. Okay, so tangent squared x plus 1, that's equal to secant squared x. So this is, I'll write it over here, that's secant squared x quantity squared, and that is secant to the fourth x, and that's it. That's the end of the story. All right, I hope you can follow all those examples, and that should set you up pretty nicely to do the first set of problems I'm assigning for today, which is on pages 463 to 464. I think my next video that I'm going to work on in a few minutes, I'm going to try with my document camera. And so you're not going to really see my face too much. Instead, you'll see my hand working out problems, and I'll be talking over it. All right, good luck. Take care. Bye-bye.